lighting seems very poor. Huh?
Yes, sir.
You cannot make it bright.
This
More lighting?
only light we have, sir.
Because
If I reduce then
switch off all. Switch off all. No, it's worse than very worst.
yes, sir.
Can you remove that curtain?
So that board will be reflected, sir.
Here you can otherwise.
I'll try that one, sir.
Huh?
I'll try that one. Sir.
Yeah, at least. Yeah, somewhat okay. You remove completely cannot. No. You cannot open completely.
Completely?
Just move, no? It is possible. No space. Yeah, it is somewhat. The brightness is coming. It is better actually. It seems better. Still, that one also you can little bit. It's okay. I think it's not much, but it is okay.
It is set.
Already it is recording.
Yes, sir. That one will be editable.
Oh, editable, huh? Okay. Okay, under the theory of angular momentum in the last class we have discussed the action of raising operator L plus acts on a state vector L comma ML which are represented with a quantum number L and ML. So we have determined the probability density value C plus when L plus acts on the state vector L comma ML. Now let me continue from the same concept to find it when the lowering operator L minus if acts on the state vector L comma ML to find it the probability density C minus probability density C minus for finding out the probability density C minus, we have to take the expectation value of the product of L plus and L minus, the composition of L plus L minus. In the state of L comma ML. But we know that this combination L plus and L minus is nothing but L x square plus L y square plus H cross Lz. If we place this value from here to here, then L plus L minus the expectation value of combination of L plus L minus and Lx square plus Ly square plus H cross Lz L comma ML. Brown kit. Fine. Let us expand the term L comma ML with Lx square. Sorry. Further, we know that the total angular momentum L square is also nothing but Lx square plus Ly square plus Lz square. Sum of square of angular momentum in all the component x, y, z. From here, one can easily find out the value of Lx square plus Ly square. So, L square minus Lz square, if you take it this term from here to here, then Lx square plus Ly square. Now again, you feed this value from here to here, we can write L plus L minus as L comma ML, then Lx square plus Ly square is nothing but L square minus Lz square plus H cross Lz, then L comma ML. Now we had to expand the term L comma ML, L square, only first term, and then ML with negative sign here to put ket and bra vector here, each and every term. L comma ML, Lz square, L comma ML, again plus H cross Lz is there. So H cross is nothing but the constant we can keep outside. Then L comma ML, Lz, L comma ML. So the total angular momentum acts on this state vector L comma ML will give you the eigenvalue with the new eigenstate. Then for writing that, L comma ML, if L square acts on this total angular momentum, so if we will get it L into L plus 1 H cross square, then state will be retained. This is nothing but the eigenvalue of operator L squared. This is nothing but eigenstate of the total angular momentum L squared. Similarly, for writing the second term minus L comma ML, it is L square Z operator acts on this state, so it will act on ML. So in that case, we will get it L square H cross squared, ML square H cross squared L comma M L. Again plus, already one h cross squared is in outside, L comma M L. L is at acts on ML to give you the eigenvalue as M L H cross, then state will be retained. Then we know that this is actually nothing but a number. Again, this is also a number, this is also a number. We can take this constant value h cross squared L comma M L, L comma M L, and here if you take it out, M L squared h cross squared L comma M L, L comma M L. When you come to this term, already one h cross squared here, if we take out this, then we will get it M L h cross squared L comma M L, L comma M L. Of course, as per the chronic this value will be 1, again this value will be 1, this will be 1. Then if you simplify, we will get L into L plus 1 h cross squared minus M L squared h cross squared plus M L h cross squared. If we take it h cross squared outside, M L squared M L, then further we can also reduce L into L plus 1 minus, so minus ML you take it outside, so one can write it ML plus 1 h cross squared. This is nothing but L plus L minus expectation value is nothing but C minus this is nothing but L comma M L, L plus L minus L comma M L. But the L plus is complex conjugate of L minus. This is bra vector, this is kit vector. Then if you are writing the bra vector into a form of kit, then L plus is the complex conjugate of L minus. So L minus, so this bra will be written in kit L comma M L, then again L minus L comma M L. This can be further written as L minus L comma M L determinant square. As we discussed earlier, the value of L minus operator, lowering operator, acts on a state vector L comma M L will gives the probability constant C minus with the state vector L M L minus 1. If you take the square of this equation, then one can write it L minus L comma M L is equal to C minus L comma M L minus 1. Further, this expression, the last expression, can be written L minus L comma M L is nothing but C minus determinant square L comma M L minus 1 determinant square. When we compare this equation here, L minus L comma M L is nothing but here this two, this one, this two, then is nothing but L into L plus 1 minus M L into M L plus 1 H cross square. If we place this value further, for expanding this equation, L minus L comma M L whole square is nothing but C minus determinant square. This value will be 1. This value is nothing but L comma M L minus 1 L comma M L minus 1. Then this value will become 1. Then L minus L comma M L determinant square is nothing but C minus whole square. If we feed this value from here to here, then we can write it C minus determinant square is nothing but L into L plus 1 minus ml of ml plus 1 h cross squared. Then for finding the C minus value, the probability constant for the lowering operator L minus is C minus L into L plus 1 minus m L into m L plus 1 and the square root h cross squared, or h cross. This is nothing but the probability density of lowering operator when L minus acts on state vector L comma m L. So finally we can write the L plus the raising operator acts on a state vector m L. It gives a probability constant C plus and the ml quantum level of ml move to one notch up. So C minus is nothing but L into L plus 1 minus m L into m L plus 1 under square root, so h cross L comma m L plus 1, and the lowering operator L minus acts on the state vector L comma m L to gives the probability constant C minus with L comma ml minus 1. The ml lower one quantum level. In this case, the probability constant C minus for lowering operator is nothing but L into L plus 1 minus m L into m L minus 1 h cross L comma m L minus 1. If you are writing combinedly, L plus minus L comma m L is equal to L into L plus 1 minus m L into m L plus or minus 1 under square root h cross L comma m L plus or minus 1. Fine. Now let us write the angular momentum operator Lx and Ly in terms of a quantum number state vector L comma m L. Suppose Lx acts on m comma m L. We can write the value of Lx is nothing but defined from this value of Lx can be defined from the sum of the raising and lowering operator. For example, the L plus is nothing but Lx plus I Ly and L minus is nothing but Lx minus I Ly. L plus is the complex conjugate of L minus, vice versa. Now if we add these two, L plus plus L minus, we will get it to 2Lx. Then the value of Lx can be written as 1 over 2 L plus plus L minus. Then if we feed this value here, 1/2 L plus L minus state vector L comma M L. Then 1/√2 L plus acts on M L plus L minus acts on again the state vector L comma M L. So we know that L plus acts on this state vector, it gives the probability constant with C plus with the state vector L and M L plus 1. Similarly, if L minus acts on this state vector, then we will get the probability constant C minus with the state vector L comma M L minus 1. Here one quantum level will move up and here lower the one quantum level down. Magnetic orbital quantum number ML. This is a total orbital angular quantum number L. Then 1/√2. So C plus is nothing but L into L plus 1 minus M L into M L plus 1 under square root H cross L comma M L plus 1. This is what here. Then plus C minus is nothing but L into L plus 1 minus M L into M L minus 1 under square root H cross again L comma M L minus 1. Close the bracket. This is nothing but Lx value. Lx operator acts on state vector ML. Further, for writing the Ly operator in terms of raising and lowering operator or the quantum numbers state vector, Ly acts on L comma M L, but we know already the L plus, again it is called Lx plus I Ly, and L minus is nothing but Lx minus I Ly. If we subtract these two equations, we will get the value of Ly is nothing but 1/2I Lx minus I Ly. Sorry, L plus minus L minus. Then if we feed this value here, 1/2I L plus minus L minus with the state vector L comma M L. Again 1/2I, so L plus acts on the state vector M L minus L minus acts on this state vector L comma M L. So as we know that L plus, when it acts on this state vector, we will get the probability constant C plus with L comma M L plus 1 quantum level, then minus L minus acts on L comma M L we will get the probability constant C minus with the one quantum number ML lower. Further, if we write C plus L into L plus 1 minus ML into ML plus 1 under square root H cross L comma ML plus 1. Here minus, the C minus is nothing but L into L plus 1 minus ML H cross again L comma ML. This is nothing but Ly acts on a state vector L comma ML. Sorry, this may be ML minus 1. Okay. Further, for extending the Hermitian operator and non-Hermitian operator in the form of matrix or the matrix representation of all the Hermitian non-Hermitian operator such as Lx, Ly, Lz, L squared and L plus L minus, we have to apply the orthogonality condition between two different angular momentum L and L dash. Take two different angular momentum L and L dash and apply the orthogonality condition between these two angular momentum L dash M L dash L comma M L is nothing but L dash L M L dash M L. According to Kronecker delta function, we can write it this as a delta L dash L and delta M L dash M L. Let's start with the writing of total angular momentum L squared in matrix form. So, the matrix representation of L squared we have to take the expectation value of L squared with different angular momentum L and L dash. Then by using an orthogonality condition, L dash M L dash L squared L comma M L. So, the total orbital angular momentum L squared acts on the quantum state L here to gives eigenvalue L dash M L dash. The eigenvalue when L squared acts on this state L into L plus 1 H cross squared L comma M L. Of course, this is nothing but a constant. We can take outside L into L plus 1 H cross square L dash comma M L dash and L comma M L. Further, it can be written L into L plus 1 H cross square L dash L and M L dash M L. Suppose if we are implying the value of orbital angular momentum L is 0, then the spin angular momentum M L is also 0. Then the dimension of this matrix is 0. And for further L equal to 1, then the spin angular momentum having a 3 possible value 1, 0, minus 1. If we apply the permutation with M L and M L dash, the dimension of the matrix will be 3 by 3, that means 9 total entries will be in this matrix. Let us assume the value of L and L dash is nothing but 1. If value of L equal to 1, then the M L is also 1, 0, minus 1. When the value of L dash is equal to 1, then M L dash is also 1, 0, minus 1. If we imply this condition with this expression here, then L dash though will be 1. L into L plus 1 H cross square, here this will be 1, and here there are different possible permutation is available between M L dash and M L. So that we can make it as matrix form. This will be 1. Now for constructing the matrix, L into L plus 1 H cross squared, keep it this one, and here this one, it will be 3 by 3 matrix. So total 9 entry will be there. You take it M L in row and M L dash in column. Write the possible values of M L in row 1, 0, minus 1, and all the possible values of M L dash you write it in row column 0, minus 1. Now the inner product will actually takes place between different values of M L dash and M L to construct the 3 by 3 matrix for the value of L equal to L dash equal to 1. Then further this matrix can be written H cross square ML ML dash 1 0 minus 1 1 0 minus 1. Put this value here, L into L plus 1 inner product between ML dash and ML, as ML dash is 1 and ML is 1, so inner product between 1 and 1, and L into L plus 1. If you put the value of L equal to 1 and 1 here, so we will get it 2. This entry will be 2. Further, if you are writing L into L plus 1, the inner product between 1 and 0, 1 and 0 inner product. But the value of here L equal to 0, then if we put this L equal to 0, the entire term will become 0. Then this will be 0. And when you come to the inner product between 1 and minus 1, then L into L plus 1, 1 and minus 1. And according to the Cronquist delta function, the inner product between two different states will be a 0. Then the product of this will be 0 again. Comes to the inner product between L into L plus 1, 0 and 1. Again, if you look at as per the Cronquist delta function, this will be 0. And when you come here, L plus 1, 0 and 0. So this value will be 1 and the value of L is 0, then the entire value will be 0. Coming to this point, again this will be 0 and this entry will be 0 and this entry will be also 0. Then inner product between these two, the value of L is minus 1. In other words, we can also calculate Coming to here, the value of L equal to 1, so this product again it will be 1. 1 plus 1 H cross square, then this matrix will be here. ML, ML dash, 1, 0, minus 1, 1, 0, minus 1. So the inner product between 1 and 1, inner product between 1 and 0, inner product between 1 and minus 1. Again 0 with 1 inner product, and here 0 with 0. Again it is here 0 with minus 1. When you come here, minus 1 with 1, and here minus 1 with 0, and here minus 1 with minus 1. According to Kronecker delta function, this matrix can be further simplified. So L squared is nothing but H cross squared. This value will be 1, this value 0, this is also 0, this is 0, 1, 0, 0, 0 and 1. All the diagonal elements only having valid entry. 1, 0, 0, 0, 1, 0, 0, 0, 1. Similarly, for writing the matrix representation of other operator, Hermitian operators Lx, Ly and Lz, consider the Lz. L dash and L dash, according to the orthogonality condition, we can write the expectation value of Lz when Lz operator acts on this quantum state. We can get it the eigenvalue with M, L, H cross and L comma M, L. Then we can take it out, this M, L, H cross outside. L dash, M, L dash, L comma M, L. Further can be written L dash L, M L dash M L. Now if we imply the value of again L equal to L dash equal to 1, then this term will become 1. For writing the matrix representation of Lz, further it is simplified as M L H cross M L dash M L. So M L H cross, take it M L in row and M L dash in column. The values 1, 0, minus 1, again 1, 0, minus 1. Or we can also, instead of writing like this, we can also write it 1 ML 1. So we can put ML inside with the inner product. Again it is here 1 ML 0, and when you come here this entry 1 ml minus 1 and comes to here 0 ml 1 and 0 ml 0 1 0 ml minus 1. For writing the inner product with minus 1 and 1, minus 1 ml 1 again minus 1 ml 0 and here again writing minus 1 ml minus 1. Then H cross so the value of ml is nothing but 1 here, so the inner product between 1, so if you take it 1 outside, then this term again 1, inner product between 1 and 1. So the final answer for this entry will be 1. When we come here, the ml value is nothing but 0. Whatever the inner product, if multiplied by the ml with 0, then this entry will be 0. And when we come here, the ml value is minus 1, so we can take it outside as minus 1, but the inner product between two different quantum level will give you 0, then the final product is also 0. Comes to here, again the same, it will be 0. And if you look here in this particular entry, ml is 0 and inner product between the same state will give you 1, but if we multiply with the 0, ml equal to 0, then this entry will be again 0 and this one is also 0, here 0, 0, but when you come here, the ml value is minus 1 and inner product between similar state, so we will get it minus 1. So the value of Lz is nothing but H cross 1 0 0 0 0 0 0 0 minus 1. For writing the value of L plus non-Hermitian operator L plus with orthogonality condition, we can write L comma m L dash L plus L comma m L. So we know the value of L plus is nothing but this one, it will be C plus L comma ml one notch up with the spin quantum number. Then the value of C plus is nothing but L into L plus 1 minus m L into m L plus 1 under square root H cross, then the orthogonality m L dash L comma m L plus 1. Again the same expression further can be reduced, L into L plus 1 minus m L into m L plus 1 H cross L dash with L and m L dash with m L plus 1. Now if we imply the value of L is nothing but L dash is nothing but 1, then in this expression, above expression, keep it to the value of L and L plus 1 or is 1. So this will be 2 minus m L into m L plus 1 H cross this value will be 1 with 1 inner product and m L dash m L plus 1. So this will be 1. Then we can remove it, this value. So finally it can be written as m L dash m L plus 1. For further developing the matrix representation, keep it H cross here outside, then take m L and m L dash here. So if m L is nothing but 1 0 minus 1, then we have to write it m L plus 1. So m L plus 1 is nothing but 2 1 0 and m L value 1 0 minus 1. So the inner product will be developed like this. Then multiply with this term square root of 2. I am calculating the first entry here, square root of 2 minus m L into m L plus 1. So H cross is there, it's as a common in outside. Then the inner product between 1 and 2. Now if we put the value of m L is as 1 here, ml, if you put 1, then it will be square root of 2 minus 2, again this term will be also 2, then the final answer will be 0. Coming to the second entry, here inner product between 1 and 1, m L dash is 1, m L plus 1 is nothing but 1, then square root of again 2 minus, so m L value is nothing but 0, then this entire term will be 0, this entire term will be 0, so only we have square root of 2, then inner product between 1 and 1, so we will get it square root of 2 is as answer. Coming to the third entry here, square root of 2 minus m L is nothing but minus 1 and this is minus 1 plus 1 will become 0, then 0 with anything 0, then we will get it to square root of 2 only, and inner product between 1 and 0, so according to Kronecker delta function, again inner product between two different states will be 0, then this entry will be 0. Comes to inner product between 0 and 2, then square root of 2 here, the value of L is nothing but 1 again, so here this will be again 2, then 2 minus 2 will give you 0, and inner product between 0 and 1, again this answer will be 0. When you come to the inner product between 0 and 0, we can expect some valid entry here. However, square root of 2, the value of ml is 0, so this entire term will be 0. Then square root of 2 only will be there. Then inner product between 0 and 1. So this term is again 0. When you come to the sixth entry here, inner product between 0 and 0, then square root of 2 minus L value is nothing but minus 1, then write it minus 1 plus 1, then inner product between 0 and 0, ml and ml plus 1, sorry, this is ml dash, this is ml plus 1. Then if you look here, this is square root of 2, then this term will be 0, minus 1 plus 1 will be 0, then inner product between 0 and 0 will be 1, so we will get it to square root of 2. Similarly, other entries, all are, we will get to 0 only. So the matrix representation of the raising operator L plus is nothing but H cross square root of 2 H cross, we can take square root of 2 outside, then 0, 1, 0, 0, 0, 1, 0, 0, 0. Again, for writing the matrix representation of lowering operator L minus with orthogonality condition, then we know that L minus acts on this state vector will give you again ml dash C minus L and L minus 1. Then the value of C minus is nothing but L into L plus 1 minus m L into m L minus 1 under square root H cross, then inner product between L1 L dash and m L dash and L comma ml minus 1. Again L into L plus 1 minus m L into m L minus 1 H cross, then L dash L m L dash and m L minus 1. Further, if we imply L dash equal to L equal to 1, then this term will be 1. So the matrix entries always come between inner product of m L dash and ml minus 1, and this equation again here, this will become square root of 2 minus m L of m L minus 1 H cross, then m L minus 1 m L dash 1 0 minus 1, and here if we write it ml as 1 0 minus 1, then ml minus 1 can be written 0, 0 and ml, so this will be -1 and this will be -2. Of course, here the inner product between two different state 1 and 0, so we can expect this answer as 0. Again the inner product between m l dash and ml minus 1 as -1, so it will be 0. Again 1 minus 2, it will be 0 here. And when you come here, so inner product between the same state, it may be the valid entry here. Then we have to find out the coefficient, what will be that. So for finding the coefficient, so square root of 2 is already there, minus m l value is nothing but for this entry is 1 here. So put it 1 and 1 minus 1, then 0 with 0. Then this value will be 0, then remaining we will get it square root of 2 with inner product of 0 and 0. Then we have valid entry as square root of 2 here, and again this will be 0, this will be 0. When you come to the seventh entry, -1 and 0, it will be 0. -1 with -1, we can expect some valid entry here. And for finding the coefficient, again square root of 2 minus, so m l is nothing but 0, so the entire term will be 0. Then inner product between -1 and -1, so the coefficient for this particular entry is square root of 2. So the last entry will be 0 again. So finally, for writing the L minus operator in terms of matrix representation 0, 0, 0, 1, 0, 0 and 0, 1, 0. If we know the matrix representation of raising operator and the lowering operator, one can easily write the matrix representation of Lx and Ly. Because the value of Lx is nothing but L plus L minus, then we know the value of L plus is nothing but this one, square root of 2, so H cross 0, 1, 0, 0, 0, 1, 0, 0, 0 plus again square root of 2 H cross, the lowering operator will give you 0, 0, 0, 1, 0, 0, 0, 1, 0. Here square root of 2 H cross is a common, we can take it out. If we add these two matrix, we will get 0, 1, 0, 1, 0, 1, 0, 1, 0. And similarly, for writing the matrix representation of Ly operator is nothing but the difference of raising operator and lowering operator. Then square root of 2 H cross 0, 1, 0, 0, 0, 1, 0, 0, 0 minus 0, 0, 0, 1, 0, 0, 0, 1, 0 for Lx value, sorry, L minus value, then finally we will get it square root of 2 h cross 0 1 0 minus 1 0 1 0 minus 1 0. Oh, Lx is nothing but 1 over root 2. Then if it is 1 over root 2, then this equation is h cross divided by square root of 2. You will get 0 1 0 1 0 1 0 1 0, and similarly here 1 over 2i, then 2i, then h cross square root of 2i 0 1 0 minus 1 0 1 0 minus 1 0. So this reciprocal of I can be written as a minus I. If it is coming as minus I, further can be written as h cross by 2 this 0 minus I 0 I 0 minus I 0 I 0. Suppose for a spin off particle, if we want to consider and to write the matrix representation, say example, the value of S equal to S dash equal to 1 by 2 for spin of particle. Then for writing the total spin angular momentum S squared can be written as S m S dash S squared S and ms. For this case, we know the total spin angular momentum S squared acts on the state vector S comma m s. It gives the eigenvalue as S into S plus 1 h cross squared, then S dash comma m S dash and S comma m S. Already we have the value of S and S dash is equal to 1. Then the value of m s have two possible value. One is plus 1 by 2 and minus 1 by 2. There are two possible magnetic quantum number. In that case, this equation further can be written S into S plus 1 h cross squared, this one S dash S, m S dash m S. If you put the value of S and S dash as off, then this will become 1 and 1 by 2 plus 1 h cross squared, this will be 1 and m S dash m S. So 3 by 2, then 3 by 4 we will get it h cross squared. Then here ms m s dash will be 1 by 2 minus 1 by 2, 1 by 2 minus 1 by 2. These are the possible value, and the dimension of the matrix will be 2 by 2. Then inner product between 1 by 2, 1 by 2 and 1 by 2 minus 1 by 2, and here minus 1 by 2, 1 by 2 and minus 1 by 2 minus 1 by 2. So further can be written this value of total spin angular momentum S squared as 3 by 4 h cross squared. This will be 1 0 0 1 as 1 0 0 1. For writing the spin angular momentum in z direction, spin angular momentum in z direction, so the by using orthogonality condition can be written this spin angular momentum in g direction is as s dash ms dash sz s ms. Now the operator sz acts on the state vector s comma m as will gives as m s h cross inner product s dash and m s dash s m s. Then keep it m as h cross s dash s, again m s dash m s. If we imply s equal to s dash equal to 1 by 2, then this value will be 1. Then we have the matrix between m s dash and m s. For writing that h cross I am keeping outside, then m s dash, the values of 1 by 2 minus 1 by 2, 1 by 2 minus 1 by 2. So 1 by 2 ms 1 by 2. This ms is coming inside. There is one additional ms is here. We have to multiply. Then 1 by 2 ms minus 1 by 2. Then when you come to write here minus 1 by 2 ms 1 by 2, and for writing the fourth entry minus 1 by 2 ms 1 by 2. If we apply the value of ms here in the inner product, then this will be 1 by 2, and inner product between 1 by 2 1 by 2 will give you 1. Then the final value for this entry is nothing but 1 by 2. But here the inner product between two different states will give you 0. Again the inner product between these two different states, it will be 0. But in this case the inner product between same state, but the value of ms is minus 1 by 2. So this entry is nothing but minus 1 by 2. For writing sz, one can take it, this is 1 by 2 outside. So h cross by 2, then 1 0 0 minus 1. Again for writing the raising operator s plus with orthogonality condition S dash M S dash S plus S comma MS. You have another pen?
in the chair.
When the raising operator acts on this state vector S comma MS, we will get S dash M S dash S comma MS plus 1 with the eigenstate as S into S plus 1 minus M S into MS plus 1 under square root then H cross. Then S into S plus 1 minus M S into M S plus 1 H cross under square root S dash S M S dash MS plus 1. By using this condition S equal to S dash equal to off, then this value will be 1. Coming to this term S equal to 1 by 2. So 1 by 2 here 1 by 2 plus 1, so 3 by 2, so we will get it 3 by 4 under square root, and we don't know MS, it will comes under the permutation, so keep it as such, and H cross. Now the matrix entries will involve between MS and M S plus 1, so write it MS here and M S dash here. So the value of M S dash is 1 by 2 minus 1 by 2, and M S is nothing but 1 by 2 minus 1 by 2, and M S plus 1 is nothing but, if we add, then it will be 3 by 2, then minus, so this will be 3 by 2 here, and here it will be 1 by 2. Then involved between these two states. So 1 by 2 I am writing here this entry 1 by 2 with 3 by 2. So MS dash is 1 by 2 and MS plus 1 is nothing but 3 by 2. Then in between this term is also coming, coefficient is coming here. So if we put MS is 1 by 2 here, so 1 by 2, then another 1 by 2 plus 1, so 3 by 2, 3 by 2 with 1 by 2, 3 by 4. So the net value will be 0, the coefficient will be 0. So if coefficient is 0, inner product whatever, that will be 0. Now coming to the inner product 1 by 2 and 1 by 2 with the coefficient we had to calculate. Here it is a minus 1 by 2. So square root of 3 by 4 minus, this is minus 1 by 2 and minus 1 by 2 plus 1, then 3 by 4, here 1 by 2, then we will get 1 by 4, then if you multiply it will give you 3 by 4 plus 1 by 4, so we will get it 4 by 4 under square root is nothing but 1. So here the inner product is between 1 by 2 and 1 by 2. So this will be 1. Similarly, for writing the inner product between minus 1 by 2 and 3 by 2, we will get 0. And when we come to here, the inner product between minus 1 by 2 and minus 1 by 2, minus 1 by 2 and 1 by 2, then this will be also 0. Similarly, for calculating the value of S minus operator, so S plus operator is nothing but 0, 1, 0, 0, and S minus operator, it will give you then the eigenvalue of S minus operator acts on the eigenstate S comma ms is nothing but S into S plus 1 minus m S into m S minus 1 under square root h cross. So h cross is here, then S dash S m S dash m S. This term will become 1. Again this will become 3 by 4 minus ms of ms minus 1 h cross ms dash ms. For writing in matrix form, square root of 3 by 4 minus ms of ms minus 1 h cross, then here this is ms plus minus 1 will come. So ms and ms dash, so 1 by 2 minus 1 by 2 and 1 by 2 minus 1 by 2 ms minus 1. So if we write it minus 1, here it will be minus 1 by 2, here minus 3 by 2. So coming to this entry here, so inner product between 1 by 2 and minus 1 by 2 will 0, 1 by 2 and minus 3 by 2 will be 0, minus 1 by 2 minus 1 by 2 have valid entry, and here minus 1 by 2 and the minus 3 by 2, here it will be 0. Then for finding the coefficient of this particular term, so already 3 by 4 is there, then ms value is 1 by 2, 1 by 2 and 1 by 2 minus 1, so minus 1 by 2, again this will be become 1 coefficient. So S minus is nothing but h cross 0, 1, 0, 0. Now we know the value of S plus, S minus raising and lowering operator for spin off system. Then for finding the S x value is nothing but 1 over 2 S plus S minus, then 1 by 2 S plus is nothing but h cross, then h cross I am keeping outside 0, 1, 0, 0 plus S minus is nothing but 0, 0, 1, 0. This value will give you h cross by 2, 0 1 1 0 is nothing but yes x operator. Then for finding the yes y operator, we have to take the difference of raising and lowering operator. S y is 2i sx minus s plus minus s minus, then 1 over 2i, this is 0 1 0 0 and minus here 0 0 1 0, we have to subtract. So 1 over 2i 0 1 minus 1 0, or if we take it, this reciprocal of I will give you minus I, so h cross, then h cross by 2 0 minus I 0 is nothing but yes y operator. Find that all the matrix representation of the angular momentum operator S L square, Lx, Ly, Lz and L plus and L minus, as well as the matrix representation of spin angular momentum operator called total spin angular momentum S squared, spin angular momentum along z direction, spin angular momentum along x direction and y direction, and the spin angular momentum raising operator such as S plus and S minus, all are has been represented with matrix. That's it. Bye. Where he went? Hello.